I am Anuradha Mathur. I have been teaching physics at Modern School Vasant Vihar in New Delhi. We are going to learn about magnetic properties of materials. We are going to classify them under different heads. We are going to see how we do this classification, what is its basis. We have learned that electric currents, moving charges are associated with magnetic field. In an atom, the electrons are moving and the moving electrons form the current. Therefore, every electron in any atom is associated with a magnetic field. If we look at an orbit and an electron, let us say, and let us consider an anti-clockwise direction for it. In this anti-clockwise direction, the magnetic dipole is set up in the direction of the arrow. Its value is given by I into A, where I is the current on account of the electron movement and A is the area of the loop that it makes. Here the loop would mean and be identified by the orbit. Therefore, in a bulk matter, you have a large number of electrons and a large number of atoms to deal with. Therefore, you will have to say that all these magnetic moments are going to be added vectorially, and as such you can describe magnetization for it as the net dipole moment per unit volume. Therefore, all materials are magnetic. How do we classify them further? What happens to them in an external magnetic field? How much of magnetization is changed within them are going to be our governing factor. I have a solenoid over here. This solenoid will generate a magnetic field in its core given by B is equal to mu naught Ni, where mu naught is associated with permeability of the core inside. We have nothing here, it is just air. We can take it to be nearly vacuum therefore, and N is the number of turns that I have on the solenoid per unit length. Also the current that I pass through it is my I value. So, the field that is generated here is on account of the current flowing through the solenoid. Within this a magnetic field is generated, and if I were to place different materials in this, I can either increase this field or decrease this field, which would mean that what is the contribution of the material for increase or decrease of the magnetic field inside the solenoid. We can then form a method of describing materials and how they behave in external magnetic field. We need to describe permeability. Permeability is that which shows you how much of magnetic field is allowed to pass through a material. That means in terms of the magnetic flux, how much of flux is allowed to pass through a magnetic material or any material for that matter. Let us do this small experiment and see how a magnet, this is an external magnet, which I am going to see what is the influence on this magnet by the current passing through this solenoid in the absence of any material inside it. I switch on the current in this solenoid and just hold this bar magnet. The very fact that it is being attracted towards it means that this is getting magnetized. Now, I am going to take this iron rod and insert it inside the solenoid, and you will see the influence on this external magnet. It is getting not only attracted, totally aligned, and it is getting stuck to this particular material. Whether I took the rod in this direction or reversed it, the effect would be the same. The reason for that is that the total magnetization inside this bar has contributed towards the magnetic field of this solenoid. That means some materials are going to add towards it, the others are going to decrease it. We need to describe another quantity which is called susceptibility. Susceptibility is the measure of how much of magnetization is produced by the external field. So, if I say talk about it as m, then m is equal to xi times h. Xi is how we represent susceptibility, and it tells us how much of magnetization is developed in the material per unit external magnetizing field. H here is Ni, and therefore, m upon h is going to be my value of xi. Its unit will be cancelled, there will be no unit for it. The unit for magnetization is ampere per meter, and so is it for H, ampere per meter, and there would be no unit for our values of susceptibility. Let us see totally in effect how is this net magnetic field that is generated inside the core of this solenoid calculated if I were to add the magnetic field generated due to the current in the coil and due to this additional material that we placed inside it, for which susceptibility may be given as xi. This value can be written as B is equal to mu naught H plus mu naught M. Mu naught H is the contribution by the current in the solenoid, and mu naught xi H is going to be that due to the material. So, B is equal to mu naught 1 plus xi H, or mu r is equal to 1 plus xi. What is mu r? Mu r is relative permeability. That means, you compare the permeability of the material to that of vacuum. That means, how much more is the allowance for the flux through a material is governed by the relative permeability. Obviously, permeability and susceptibility should be related, and this is our relationship, mu r is equal to 1 plus xi. Let us find an explanation for all this. How come we have this relationship? How come we can treat materials in terms of the magnetization that is produced inside it? We have what is termed as domain theory. Now, let us describe what a domain is. A domain is nothing but a cluster of atoms within the material for which the dipole moments are in one particular direction. That means, vectorially adding up the contribution of dipole moments created by individual electrons in the sample is going to be in a particular direction. So, in a sample you may have atoms up to 10 raised to the power of 11, and these are going to be showing a dipole direction in a particular way, and this can then be contributed and seen for the entire material. As per domain theory, the alignment for different domains may be different in a sample, and these may become aligned in a particular direction when placed in an external magnetic field. The response of the material to change the orientation of the dipole moments in different domains for a particular alignment is going to be our reason for classification. We have materials which do not allow this, or in effect change the orientation in a particular way, in a way kind of repel it. That means, the orientation changes, but an effect of repulsion to the external field generates. Such materials are classified as diamagnetic substances. Examples of these are oxygen, aluminum, sodium, platinum, etc. Some of the common materials these are. You can have a situation where the susceptibility and permeability are both positive, which means that the alignment for the dipoles is in the direction of the external field. Whether it is of small value, That means value of susceptibility being slightly positive, and these values are going to make the material paramagnetic. If it is very high, like we had in the case of an iron rod, then we term it as ferromagnetic substances. So, like we had classifications of material on the basis of density, on the basis of its state, etc., we now have a new classification of materials on the basis of material reacting to an external magnetic field, or in turn its magnetic property. So, we have three classifications: diamagnetic, paramagnetic and ferromagnetic substances. Diamagnetic substances which tend to repel the influence of the external field. They have a negative susceptibility. They are going to align perpendicular to the external field. Their permeability is very, very low. And if you were to describe paramagnetic substances, they have a positive susceptibility. They have allowance or more permeability for the flux to pass through the material. They can easily be converted into magnets and form a basis for using them in useful ways. You have ferromagnetic materials for which susceptibility is extremely high, permeability is very, very high, and they easily can be magnetized, they can become magnets. So, when we are looking for temporary and permanent magnets, we have to choose materials depending upon what our requirement is. Do you think temperature could change all this for a material? Well, yes. You describe Curie temperature, which is the temperature at which a ferromagnetic substance becomes paramagnetic, or a paramagnetic substance tends to becoming a diamagnetic substance. These temperatures are usually very, very high. For iron, this temperature is about 770 degrees Celsius or 1043 Kelvin. We have learned a new way of classification of materials. We have been doing that in terms of density, in terms of state, solid, liquids and gases. This time we did it in terms of the magnetic property. That is, what happens to a material when placed in an external magnetic field. That each material has an associated magnetic field inbuilt inside it due to atoms and the electrons that move in them. Every electron in the orbit moves, it has an associated magnetic field, there is an associated dipole moment, there is a net vectorially added dipole moment per atom, and therefore, we can describe the material having domains, and on the basis of all this we have materials that we are classifying as diamagnetic, paramagnetic and ferromagnetic. This is all for making use of materials in different ways for making permanent and temporary magnets.